pleasure of introducing our speaker today, Professor Seitzinger. Right? All right, thank you. Yeah, so, and she's a professor and director, executive director at UVic. Second point, she's currently executive director of the Pacific Institute for Climate Solutions and professor at the School of the Environment, UVic, as I said. Her research is on land, atmosphere, ocean, geochemistry. I definitely needed the notes. I couldn't have done this yet. And she's here.
Thank you. Well, it's a pleasure to be here today, and thank you for that introduction. I'll just wanted to start, before I start my talk on nitrogen, I just wanted to let you know about a funding opportunity that we announced in August of this year. It's a new opportunity called the Pacific Institute for Climate Solutions, or PICS, Opportunities Projects. And we're going to do an information session on that this afternoon over in the Sears building at 1:30, and you're all welcome to come. The Pacific Institute for Climate Solutions was started in 2008 by a very generous endowment from the BC government. And we are independent from the government, and we are located at the University of Victoria, but it's a collaboration across UVic, UBC, SFU, and the University of Northern British Columbia. And we fund research that is addressing climate solutions, so mitigation and adaptation, and that we do this in collaboration across faculties in the universities, but also with users of that information. And so this new funding opportunity is an opportunity to submit proposals that need to be done collaboratively between faculty, students at one of these or more of these 4 universities, and with people who can make decisions from the private or the public sector that can move forward with mitigation and or adaptation. So I encourage you all to come, and we'll talk about some detail there. If you want to know more about that and you're not able to come to the session this afternoon, there's the website. And if you want to talk with me about an idea that you have in mind, you're welcome to send an email to the PICS email, and then we'll schedule a time quickly for you to be able to, within a day or two, easily you'll be able to talk with me. Now the deadline is coming up quickly. It's the 15th of October, but the proposals are not long. They're only 5 pages long, but of course with CDs and plus CDs and reference lists, etc. But the proposal process should be, is not too onerous, we hope. So anyway, I encourage you to take a look there, and or contact our PICS campus manager here at UBC, Sarah Muir Owens, and that's her email address. So with that, I'll move into nitrogen. So why nitrogen, and why nitrogen hunting from land to oceans? I think that I'm going to take you sort of a journey or a walk through time in terms of our understanding of nitrogen and nitrogen movement from land to the coastal ocean and to the open ocean. And the reason being, of course, is that, as many of you know, nitrogen is a very important element that can limit and be very important in limiting production in our coastal oceans and in our many open ocean areas as well. So, as of about the mid-90s, we were beginning to get a global picture of how much nitrogen is coming into land, our terrestrial systems. And there came estimates from Jim Galloway and others showed that there was about 100 teragrams of biological N2 fixation in terrestrial systems at the global scale. But they also showed that the amount of nitrogen, total new nitrogen coming into terrestrial systems, was actually more than double that because of anthropogenic sources. And those anthropogenic sources were from combustion of fossil fuels, emitting NOx into the atmosphere, which then gets deposited, from the use of synthetic fertilizers in agriculture, from animal production systems, as well as from biological nitrogen fixation associated with agriculture, legumes and soybeans, or such as soybeans, etc. So that we had markedly increased the amount of nitrogen coming into terrestrial systems. So that's sort of an introduction. But I want to take you back to about 1970, before we had this view, when we really were thinking primarily about the natural nitrogen on land. So in the early 1970s, it was becoming apparent that we had a problem in many of our coastal environments, many of our estuaries and some continental shelves around the world. And that problem was, we thought we knew what the problem was, or what was causing the problem. We had a number of ideas, but in many cases we were wrong, and we also really did not understand how difficult it was going to be to address this. And so the problems were algal blooms, massive algal blooms, as well as areas that were becoming anoxic or had low oxygen around the world. So the question became, what's causing, where are the nutrients coming from that are causing these algal blooms? And how much is coming in? And from what sources? And so in about the early 1980s, there was a synthesis of data from many coastal areas around the world by Scott Nixon and others, in which they showed that there was a quite good, although we notice that we have a log-log relationship here, a quite good relationship between chlorophyll concentrations in the water column and nitrogen loading from rivers to those same systems. Now this was quite controversial at the time because most of the work on eutrophication had been done in freshwater systems, and phosphorus was known to be the primary nutrient limiting production in freshwater systems. And so the idea that it was nitrogen in coastal systems created quite a bit of discussion. But more and more data was coming forward to support this, such as broad relationships such as this. So the question became then, where is this nitrogen in the rivers coming from? What are the sources? What's the magnitude? And how much of that then is getting into our estuaries? So we're going to use this figure as we go through the talk and work our way down to the oceans. So let's first look at the terrestrial to river sources. So what's the magnitude and the sources of the nitrogen in rivers that's getting into estuaries? Well, again, in the early 1980s and into the early 1990s, there were a number of budgets of nitrogen that were done in estuaries around the world. Well, actually, primarily in the US and Europe. And these would identify, as you can see, here's an example of some of them, that they had a quite well quantified point sources or sewage inputs. It's pretty easy to measure. It comes out of a pipe. But a lot of the rest of the nitrogen in rivers was just classified as diffuse. So they didn't know where it was identified as to whether that was a natural source or whether it was anthropogenic and where that was coming from. There was some work going on in the Baltic that was starting to see that a large part of that might be agriculture and or atmospheric deposition. But there were only a few budgets like this, and they're very, very time-consuming to do, to make measurements over annual cycles and over a number of years. There were only about 15 estuaries by the mid or early 1990s, mid-1990s. And so they gave us an insight into what might be going on, but they didn't give us any capability for projecting changes in the future. It also didn't really give us insight into what the sources were. And there are over 8,000 rivers coming into coastal systems around the world. So it was just would be overwhelming to try and make measurements in every estuary or in hundreds or at least thousands of estuaries to try and get a global picture of what was going on. So we formed an international working group to scale up and use a lot of the site-specific measurements that had been made to try and develop a model that could be applied at the global scale. And so this international working group pulled together all the measured river nutrient concentrations and water discharge to get the measured export by rivers, or as many rivers around the world that we could. we then looked into what the nitrogen, land use in the watersheds was, including any nitrogen inputs from both anthropogenic and natural sources. Combine that to develop a model to predict nutrient export as a function of watershed characteristics, and then applied that to global databases to get a spatially explicit view of nutrient transport by rivers to coastal systems around the world. So that's just a very high-level view. I'm not going to go into great detail, but just one more level of detail here in that model. It was called the Global News Model, Nutrient Export from Watersheds. It's still used quite extensively today. The nutrient sources in each watershed, based on half-degree by half-degree global databases, included natural nitrogen fixation, phosphorus weathering for phosphorus export. In terms of anthropogenic sources in each watershed, the non-point or diffuse sources were the use of fertilizer in each watershed by crop type and by region, because the differences in how much nitrogen is used, let's say, for corn in Asia is different than in North America, for example. Nitrogen fixation by legumes in crops, and manure production by animals, all the way from, we had camels to cows to chickens in there, a wide range of animal species, and atmospheric nitrogen deposition, primarily from the combustion of fossil fuel. As well, so those were the diffuse sources, and then the point source was sewage. And that was modeled as a function of a number of factors, including population and treatment level. So those nutrient inputs into each of those watersheds were then moved by a series of equations into the river, but using various hydrological and watershed factors, physical factors, including water runoff, which is very important in moving nitrogen from the landscape into the river, precipitation intensity, of course land use, and a number of other factors. And then once in the river, then there was in-river nitrogen and phosphorus removal in reservoirs, in the river itself, as well as removal of nutrients as water is removed for irrigation and applied back to the landscape. So that was just a sort of a brief view of what some of the inputs were into the model and how it was treated. And so that was used then to calculate for all of those watersheds river nutrient export to the coastal zone, so to the mouth of the river. And we had nitrogen, phosphorus, carbon, and silica modeled in there, and including different forms of those elements. For nitrogen, dissolved inorganic nitrogen, so that would be nitrate, nitrite, and ammonia, dissolved organic nitrogen, and particulate nitrogen. So, what did we find? Well, applying those global databases, we were able to produce for the first time a global view of nitrogen export by rivers to coasts. And the units that you see here are kilograms of nitrogen per kilometer squared of watershed per year. So it normalizes for the size of the watershed. And what you see, and what was not surprising, I think, was that we saw that there was fairly high export in the United States from the Mississippi Basin, which is very agricultural, as well as many small rivers along the east coast of the U.S. Europe, again, fairly high export in many of the watersheds, particularly in Western Europe. But what was really surprising to us, I think, was the very large export in Asia, a really hot spot in southern and eastern Asia, which up until that point we really didn't have that view of. Well, the model also allows us to look at what were the sources in each of these watersheds of the nitrogen or the phosphorus, etc. And I'll just show you first the results for the dissolved inorganic nitrogen. And on the pie diagram on the left, what you see is the global contribution of the various sources to the rivers. So fertilizer globally was accounting for about 25% of the dissolved inorganic nitrogen in the river. Animal production systems, another about 20%. Some from atmospheric deposition, a small amount from sewage or point sources, and then biological nitrogen fixation accounting for the rest. What you see in the right-hand side is where we've mapped the dominant source or the largest source of contributing to the river nitrogen in those watersheds. Of course, we have the information in the model for the source that's the second largest, third, etc. But I'm just showing you here the dominant source. And what you see is that biological nitrogen fixation is still the largest source of DIN in many rivers, particularly in the far north, throughout much of South America and Africa, where the population densities are fairly low. There's not much agriculture. There aren't a lot of very large cities necessarily. But what we do see is that fertilizer is dominating in much of North America, where we have agriculture, as well as in much of Europe, but also in southern and eastern Asia, where a lot of fertilizer is used in those regions. And then, of course, animal production systems in some specific watersheds, and a few watersheds where atmospheric deposition was the largest source. We could compare that, or actually contrast that, when we look at the phosphorus story. And for phosphorus, it turns out that sewage or point sources are the major contributor to the DIP in the rivers. People thought that sewage would be the major source of nitrogen because it is for phosphorus. And so there was quite a bit of discussion going on with this. But as you can see, throughout, there's still areas where weathering of phosphorus, so a natural source in the high latitudes and areas which have very low population densities, is a major source. And then throughout much of the rest of the world, again, it's point sources. So much easier to control the point sources than diffuse sources such as nitrogen from animal production systems and from crops, so from food production systems. Well, we've looked now at what's the magnitude of nitrogen and some cases phosphorus around the world. What are some of the sources, the dominant sources. But when that nitrogen, in this case we're going to focus now on nitrogen, when that nitrogen gets into the estuaries from the rivers, what happens to it? What's the fate of it? And how much of that then can, if it's not removed within the estuary permanently, can get discharged, exported to the continental shelf. So we're working our way from the land to the rivers to now the estuaries. And the two major mechanisms of removal, or permanent removal of nitrogen in the estuaries, of course, is burial in the sediments and denitrification. And denitrification is a microbial process, mainly occurs in the sediments, in which, during the decomposition of organic matter under low oxygen or anoxic conditions, in which nitrate or nitrite is reduced to nitrogen gas or nitrous oxide. That gas then diffuses out of the water into the atmosphere and is removed from the system. And so we were just beginning also at that point to get a much better understanding of the magnitude of denitrification in estuaries. So we started to look at how much of the nitrogen can be removed in estuaries versus how much then is left over for being exported to the continental shelf. So we pulled together a lot of information, a lot of measurements of denitrification, some of which we had made ourselves, but a lot of other measurements from other people as well, for all the systems in which we had data at that point, and that was in the year 2000. And what we saw was that, again, I point out that this is a log scale, but what we saw that in general was that nitrogen removal by denitrification in these estuaries was increased as we increased the nitrogen loading, as the nitrogen loading increased. So we had a fairly wide range of nitrogen loading across these systems. And that in general, about 30%, if we were to sort of wave our arms, of the nitrogen that is coming in is getting removed within the estuary by denitrification. So then about 70% then would be exported to the continental shelf. However, a little complicating factor there is that, I want to be sure I've got this right. Yes, I'm in the right order here. That not all, of course, rivers go through estuaries. There are some large rivers that discharge directly to the shelf or go blasting through a small estuary or an estuary right onto the continental shelf. And so how could we then get an idea of what the nitrogen budget was for continental shelves? How much of the nitrogen from rivers was either going through estuaries or getting directly discharged to the shelf and then being processed there before being moved into the open ocean? So what we did is first of all, we took a fairly simple approach. And it was in the mid-1990s, and we're developing that with a large group of people, a nitrogen budget for the whole North Atlantic continental shelf, both the shelf that was along North America as well as along Europe. So both sides of the shelf. We divided it into 6 different regions, took measured rates, published rates of river concentrations and discharge, measured atmospheric deposition, measurements of burial, etc. In all the data that we could find for shelves around the North Atlantic, and developed these static budgets basically. And so what we found, the conclusions of that, were that the amount of nitrogen coming in from rivers was somewhere between about 46 and 63 units, 10 to the 10th moles of nitrogen per year, coming into the North Atlantic continental shelf, so from land-based sources. That range accounts for the denitrification in the estuaries. There was about 13 units coming in with atmospheric deposition from land. So again, fossil fuel combustion, emissions from agriculture of ammonia being deposited to the shelf. So then we wanted to say, okay, well, what are removals of nitrogen on the North Atlantic shelf? And so for burial, it's quite small, only about 2 to 9 units per year. So the question became, how much of the nitrogen is getting denitrified on the continental shelf? So again, we combined all the data we could find from the literature on denitrification on any continental shelf anywhere. And unfortunately, because we didn't have nitrogen loading for all these continental shelf areas where those measurements have been made, we couldn't relate it to nitrogen loading. But we did see a relationship with sediment oxygen consumption. And if anybody wants to know why it might have been related to sediment oxygen consumption, I'll be glad to go in that at the end. But basically, the organic matter that's falling to the sediments from phytoplankton is getting remineralized in the sediments. And some portion of that oxygen consumption is used to oxidize ammonia to nitrate, which forms the substrate or which forms the oxidant during denitrification, electron acceptor during denitrification. But basically, just remember that what we had was a relationship between sediment oxygen consumption and denitrification. And because there were lots of measurements of primary production on the continental shelves, we could take those measurements of primary production and relate that to denitrification. So you do what you can when you're working with trying to extrapolate to larger areas. So when we did that, we found that we had about 140 much larger amounts more of nitrogen being removed by denitrification than was coming in from the rivers and estuaries. Now, it was surprising, but it wasn't totally unexpected in that there had been some estimates of global denitrification based on earlier measurements, just a few measurements, some rough ideas of nitrogen loading globally. And so we weren't totally surprised, but it was the first time that data had been pulled together and actually tried to look at some specific areas. And so the question became, so this was actually a very static approach. Again, it didn't provide us with any way of really looking at future conditions or a lot of detail and dynamics other than at an annual scale. So I'm sorry, let me finish there. So we still had an imbalance, right? So the balance of the nitrogen coming in then to the continental shelf, we assumed then was coming from on-welling from open ocean systems. So that the nitrogen that's being denitrified is coming from land-based sources, but an equal or larger amount we had to estimate must be coming along from the on-welling from offshore. And insight into that ocean source onto the shelves came from some work by Katja Fennell, who developed a dynamic biogeochemical hydrodynamic model of the mid-Atlantic bight, or basically from Florida up to Cape Cod, almost up to Labrador. And so they used the ROMS model, the hydrodynamic model, and I'll show you some output of this in a minute, and combine that with a simple nitrogen-based plankton model, and also then to look at the dynamics of nitrogen cycling and carbon cycling in the water column, and then used our relationship that we just saw on the previous slide for relating the primary production in the water column to denitrification to see how much was denitrified. So I'm going to run just a short animation here, and this is the output from her model. And first I'll run it through twice because it's short and it goes by quite quickly. You'll notice that in the right-hand side of the figure here, you've got the date. So we'll start in December and go through an annual cycle. First of all, what you might want to focus on the first time through is to look at the temperature and chlorophyll. So the cooler colors are either colder temperature or lower chlorophyll. The warmer colors are, of course, then the warmer temperatures and or the higher chlorophyll. And so as we go through an annual cycle, you'll see going into spring, you'll see a spring bloom, and then you'll see it progress through the year. So let me get this started. It takes 15 seconds or something, so it goes by quickly. And then I'll run it again, and we'll watch what happens with the denitrification. Whoop. There we go. So as you can see, in the wintertime, cold water on the shelf, warmer water offshore, higher phytoplankton production coming into the spring bloom, near shore, warmer temperatures throughout the summer, coming into the fall. Okay, so you see, of course, the sort of the trapping of the higher production on the shelf and the colder offshore ocean waters there. Now we'll run it again, and you can watch the denitrification. And the denitrification will stay very close to shore. A lot of it will be within the estuaries, but you'll see how that also progresses. And then we'll look at what the numbers come out to be. So in January, fairly low denitrification coming into the spring with the higher phytoplankton production. You see higher denitrification in the near shore regions. Coming into the later summer now, denitrification decreasing into the colder temperatures. And now very little denitrification in the winter. So very close to shore. So she pulled then out of that model the annual numbers. And the river nitrogen amounted to about 1.8 units of total nitrogen coming in from rivers into either the estuary or the shelf. The denitrification, again, was much larger than the river inputs, so not inconsistent with what we found by a very sort of static box model. And that there was a cross-shelf transport as you can see there, but most of the cross-shelf transport was coming in from the north in the coastal current coming along at the upper end there around Cape Cod into the mid-Atlantic Bight area. So again, pretty consistent with what we had found from a static model, but giving us a much more dynamic look into this. So this gives us a view of the mid-Atlantic Bight, but the mid-Atlantic Bight isn't necessarily typical of all continental shelves around the world. Some shelves are much narrower, some shelves are wider than this. In some cases, we have much larger rivers than we have along the east coast of North America there. So the question became, how can we understand, what approaches might there be to understanding the amount of nitrogen that is getting from our rivers into the, maybe to the open ocean, and how much is being removed in the continental shelves. Well, the challenge has been that most, in fact almost all, ocean models, global ocean models, are too coarse a resolution to pick up the dynamics on shelf systems. Certainly not in estuaries, and most of them basically black box or ignore the continental shelf. And so it's been very difficult to try and then understand how much nitrogen globally from rivers is actually getting onto the shelves and getting removed within the shelf or getting transported as we're trying to move now down from the terrestrial environment to the open ocean. But recently, Katja Fennell, again, who's now at Dalhousie University, she was at Rutgers University when she was doing that dynamic modeling that I talked about earlier, and her student, along with John Sharples from the University of East Anglia, have been working on this and come up with, I think, a very innovative way of trying to estimate how much of river nitrogen actually stays on the shelf and is processed there and gets removed by denitrification or burial, and how much gets offshore into the open ocean. And just very simply, what they've done is develop an algorithm, basically, for calculating the river plume. So how much of the river water, in this to begin with, from river discharge is getting trapped basically on the continental shelf, and how much is getting across the shelf break into the open ocean. And so their approach was to think about the Coriolis effect and how that is causing the recirculation, basically, or trapping water on the shelf. And so they looked at not only the width of the shelf, but the latitudinal distribution of the rivers, and how the Coriolis effect then would be determining or controlling to a great extent how much of the river actually gets trapped on the shelf and how much is exported into the open ocean. So what they did is they applied this model to the 5,800 rivers that we had in our global news model, used the water discharge in that model for all those rivers, and used then a global database for shelf width. Okay? And of course, knowing where the latitude of each of those rivers. And applying that equation. And so what you see here is in the red and the green, basically, circles, this is the efficiency of freshwater export. Okay? So near the equator, where the Coriolis force is very weak, right, most of the river nitrogen is getting transported across the shelf. The river water is getting transported across the shelf. And as we go away from the equator, and if you look, for example, at the east coast of the U.S., we see that much less of the fresh water, the river water, is getting exported. So somewhere between 10 to maybe 20 or 25% of the river water is getting really exported to the shelf, and the rest is getting trapped in the on the continental shelf. Only about 15 to 25, 10 to 25% is getting exported across the shelf. I don't know if I said that right. Into the open ocean, the rest being trapped on the shelf. So that's quite consistent with what we were seeing in the dynamic modeling of that region. We can also look at the, contrast a little bit, where we are here on the northwest of North America, where we have a very narrow shelf. 10 minutes? Yeah, I'm almost done. 10 minutes, or sorry, a very narrow shelf. And so we have more of the river water is being transported off into the open ocean area, and less is being trapped for longer on the shelf. And came up with the amount of river nitrogen that should be exported from the shelf to the open ocean. So again, it gave us our first global view of nitrogen transport from land across shelves or retained on shelves. So we can now put this back into the ocean framework. And when we took the range of percentages that we saw on the previous slide and the amount of nitrogen in each of those forms, we got about somewhere between 1 and 14 teragrams of nitrogen now we estimate globally is getting to the open ocean. And that's, you may wonder why we're excited about that. We're excited about that because global ocean models have either assumed that all the nitrogen in rivers gets into the open ocean or none does. So this is one of the first times we've really gotten some additional insight into the amount. And of course, it's not just rivers. We also have to look at atmospheric deposition. And we've done some work, again, a large group of people working together with some global atmospheric deposition models. And looking at how the atmospheric deposition to the oceans from land has increased over time. And you can see the pre-industrial on the left, very low deposition of nitrogen from land, whereas by 2005, greatly increased, with the NOI deposition coming primarily from fossil fuel combustion, and the ammonia primarily from agricultural sources, and the organic nitrogen from a variety of sources. It's much more of a black box. And the amount ends up being about 39 teragrams of nitrogen, estimated to be being deposited to the open ocean from land-based sources. So through atmospheric transport and deposition. So if we put that now back into this picture, we have about almost three times as much nitrogen estimated to be coming into the open ocean from atmospheric deposition as we do from rivers. Of course, there's also nitrogen coming in from new nitrogen from nitrogen fixation in the open ocean, and of course a lot of upwelling or vertical transport from deeper waters as well. But for new nitrogen from land-based sources, we have those two components. So, just stepping back, we can sort of summarize here. We see that if you remember, we started out with this big pie diagram of the nitrogen coming into terrestrial sources, total nitrogen. And from fertilizer, from biological fixation, NOI deposition, etc., which amounted to about 250 teragrams per year coming into the terrestrial environment. Of that, only about 43 teragrams gets exported by rivers to the coast, either estuaries or the continental shelf directly. So thank goodness we have a lot of nitrogen removed on land or in the rivers before it gets to our coastal systems. Of that, about somewhere 1 to 14 teragrams we think is getting to the open ocean. And so the remainder is on the shelves and getting trapped on the shelves primarily by denitrification. So hunting nitrogen from land to oceans, we see that at each step along the way, there are not only major transport, but also major removal as we move down the system. And I'll just finish by looking very briefly into the future. So what does the future hold? And just two slides. One is that we ran some scenarios with the Global Nitrogen Watershed Model, in which we used an integrated assessment model image to look at what various policy options and costs would have on the nutrient sources that would be coming in for food production and energy production, and how that would then affect the nitrogen export to the mouth of the rivers. And in the, you can see the business as usual scenario, in which it predicts that we have a fairly substantial increase in nitrogen export between 2000 and 2030. And I'm just showing you, mainly focusing on Southern and Eastern Asia, because that was an area that has very large inputs. But you can see that with very aggressive nitrogen mitigation, very aggressive nitrogen management, the increases can be very modest, or maybe even decrease those. So again, it's a modeling scenario. And just finally, how did those improvements, were those improvements achieved? We can see that there was a small, between the business as usual and the aggressive mitigation, sewage decreases amounted for a small amount of the difference between the total nitrogen coming in that region over that 30-year period. Nitrogen deposition was quite important in terms of using technological NOx controls. And also, very importantly, lower meat consumption, not no meat consumption, but just lower meat consumption, more modest, and better management or efficient management of nitrogen in agriculture itself. So there is hope, but it takes concerted effort, as it does for controlling or for decreasing climate change as well. But there is a climate change component in here, but not as aggressive as we need to be by 2050 to get our emissions of greenhouse gases basically down to essentially net zero. And that this nitrogen deposition is, in the model, is basically from fossil fuel combustion. So one could think that by 2050, if we meet our targets, that nitrogen deposition might be greatly decreased instead of only modestly decreased as in this scenario. So with that, I'll just do a quick summary. That basically only about 17% of the nitrogen that comes into our terrestrial environments from natural and anthropogenic sources gets exported by rivers to the coast. That we've had about a 2-fold increase in nitrogen export by rivers. That once that nitrogen gets into estuaries, that which does get in, about 30% is probably removed by denitrification, so it's not getting exported to the shelves. But the shelves are a very important filter for nitrogen. Any nitrogen that gets onto the shelves has a pretty good likelihood of being denitrified. And that the open oceans, while they are getting some nitrogen from rivers, that atmospheric deposition right now is much larger than the river inputs. But again, a lot of that nitrogen, half of that, of the 39, is NOx, so it's coming from fossil fuel combustion. So again, there may be great decreases in that atmospheric deposition in the future as we address climate change. So I'll stop there and be glad to answer any questions about hunting nitrogen from land to ocean.